Okay, it's nice to see you back here in this track. Our next session and our next speaker is Kelsey Hightower. He's working for CoreOS. And as you all know, Docker is all over the place, and he will show us a live demo of CoreOS using Kubernetes and as well as Docker.
All right. We're going to try something different. I'm going to reintroduce myself, and then when I come up, we're all going to clap really, really loud to get the speaker really hyped up and energetic. We're going to try that? Okay, I'm going to do it again. All right. So you guys are all awake, right? So our next speaker is Kelsey Hightower, who flew all the way over here from Portland, Oregon, in the United States to give you this demo and worked on the slides all night and didn't get any sleep. We're going to give him a warm welcome to OSDC. Thank you. All right, so I heard earlier that 80% of you are running like data centers with real servers, right? Is that true? Right, you should guys give yourself a big round of applause because you have like real servers, not like virtual unicorn machines in the cloud. So we're going to talk about building distributed systems with CoreOS. We're also going to attempt to stand up all the components that you would do inside of your data center. What's that? What's that? We're okay? All right, all right. All right, so what I did right before you guys walked in here is I Pixie booted 5 virtual machines on my laptop to kind of give us a very similar environment that if you have bare metal machines, you're going to probably Pixie them. Hopefully you're not running around a data center with CDs in 2015. There's a much better way of doing this. You can do something like Pixie. So hopefully you guys know about that. All right, so a couple of goals today. One is to provide an overview of distributed systems and distributed infrastructure more concretely. And then a live demo of CoreOS and Kubernetes. Right, so the goal here is like we have all of these puzzle pieces. Like there's tools like etcd, there's Docker, there's operating systems. But what's the point of having all these tools, right? The end game is to actually build something and build something useful. So we're going to see what all the Lego pieces look like connected together and what you can build with that. And then I want to demystify and spark your imagination, right? So a lot of people think these systems like Kubernetes. The Borg paper was released probably last week from Google. So Borg is a very intelligent cluster management system that Google used to run their physical data centers. And Kubernetes represents an open source edition of that and lessons learned. But the system is not as complicated as most people think. We're going to try to show and break that down. To get your frame of thinking correct, I want you to ask yourself this question. How would you design your data center if you could never log in, right? So a lot of our tools that we have today are basically automating the processes that we do today, right? We log into a server and we type a bunch of commands to add users and services and check on things. And what we've done over the years is just automate that process, right? So yay for automation, but we just took the workflow that we had and just wrapped something on top of it. So imagine if you could never log into your server, would you build it a different way? I think the answer is yes. So we're going to talk about distributed systems really quick. How many of you are familiar with distributed systems? All right, some of you may have degrees in it. That's cool. I don't. The way I like to describe a distributed system is a collection of machines, usually connected over a network, that act as a single machine, right? And the idea here is that you don't keep track of all the host names. You don't try to log into all the servers and you want your SSH key everywhere. You want to have that collection of machines look like a single machine. That's where things get really, really hard. That single machine view needs to be scalable. So if we were talking about a single machine, you should be able to hot plug in a new CPU and get more CPU capacity and hot plug memory while the machines are still on. This is very popular in the mainframe world. But you can also do this with a collection of servers if we can adopt some of the distributed computing principles. Highly available, machine goes down. Maybe a new one is provisioned automatically, or maybe the service running on that machine can move somewhere else. Fault-tolerant. This one's really confusing for a lot of people. Fault tolerance, in my opinion, is you have a bad actor on the network, and it joins, and it starts doing something destructive. You got to be able to protect against that. So a service is up, but it can't communicate with everyone else. We have to have some protections in place. And we'll see what etcd does with the Raft protocol to prevent some of that stuff from happening. And then we need consistency. So the consistency here is the idea that we interact with this cluster like a single machine. We try not to interact with 50 different tools. That gets really confusing, and you just start hacking things together. We want a consistent view of the cluster. Now, there are some downsides. There's pros and cons to distributed systems. The pros are there's proven solutions for fault tolerance. There's people that have researched this stuff in detail, written white papers about it, and now we're moving to an era where those white papers are actually bits that you can download and run in your own systems, right? So this is, we're moving past the theory phase and getting to the actual implementation phase. And some people have been doing this for a decade or more. It's also your best shot at 99.99% uptime, right? Some of you probably have sales reps that put that in the contracts, and you look at them like, you know, we're going to be paying everyone refunds like half the year. You know that, right? How many people know how much downtime you can have before you miss 5 nines? 5 minutes, right? So if you have like a bunch of sysadmins, right, and they're all on call, maybe you're fancy, you have something like PagerDuty, and server goes down, they get a call, they wake up really quick, and they fix it. You're like, woo, 4 minutes, 32 seconds. That means you have about 28 seconds for the rest of the year before you miss 5 nines, right? So you kind of need a system that has just this stuff built into it, right? So the cons here is the increased complexity, meaning you have to understand what you have, right? A lot of vendors say it's easy to use. No, it's not. When it breaks, it's not only going to break, it's going to break really, really fast, and it's going to break everything at the same time because it's going to be consistent. It's going to be consistently broken across all of your data center. But we build software to guard against that, so we know it's going to fail. Listen, it's going to fail guaranteed at some point. Maybe you won't be working there when it fails, but it will. There's a steep learning curve here. So when I started to get into some of this stuff, especially at CoreOS, you know, in our Slack channel, we're talking about, you know, what kind of vector clock are we going to use for this particular implementation? You're like, vector clock? You know, the Apple Watch just came out. Is this a new thing? No, like this stuff is really, really hard. But when you think about it and you break it down to its basic elements, it's actually pretty straightforward. And then software must be designed to handle failures. A lot of people have been kicking the can down the road, right? You got a database. He's like, yeah, just don't touch the database, right? So these are single points of failure. And people are just getting lazy in some cases. Like, you know what? We're just not going to fix it. We have all these sysadmins we hired. They keep it running. It goes down. They bring it back up. You know, nice compliment. But it's much better if you want to get to this 5.9 world is that you need to have your systems, you know, handle failures. I'll give you a great example. Have an application developer. They have an app that needs a database. This is simple, right? You boot the application, and it can't find its database. What should the app do? The app shouldn't segfault. You know, just don't crash and die. You can actually just look for your database and just log that you can't find it because we could be in maintenance mode, right? It could be that we just started up out of order, but there's no reason for you to have a hard failure because your database isn't there. If you just take a few seconds to protect against this, then no one needs to bring things up in order anymore. Just bring things up, and then they just kind of figure things out on their own. All right, so there's building blocks to distributed systems. I'm going to talk about things at a very high level. There's containers, and the reason why I say containers here is because I'm so happy we're not talking about RPMs, apps, tarballs, shell scripts, fabric scripts, Java, Ruby, Python. These are things that are not that important in a much larger scheme of things. You just have an application, some bits that need traffic, some data. That's the only thing that's important. It's not exciting anymore to spend your life making packages. Some people still get excited about it. But this is not the end game for what people do. Containers don't run in mythical land. For some people they do. They run on operating systems. You still need those. And then we need the network, right? These things need to talk to each other, right? So we'll talk about the network model. And then we need consensus. This is important, right? So if you have a couple of services on the network and they need to share information with each other, in many cases you want them all to agree on what that information is. This is a lot different from everyone getting the same value at the same time. This is more like if we agree at this particular moment in time that the database password is foo, we should all agree that that's the password at that time. What you don't want is two people to think the password is the same thing at the same time. That's a problem. And then a scheduler. How many people are familiar with a scheduler? So all of you actually probably have a scheduler, right? You have like these guys, they're like the sysadmins. And they know where all the servers are in the infrastructure. And if you ask them to deploy an app, they usually have this database that they keep. We call it a spreadsheet. And they take your app, they do a lookup in the database, associate it to a machine, and schedule that workload. they're pretty inefficient. They want money, they want time off. You got to feed them, but that's most people's scheduler. It's not really automated, and it's very specialized to a small group of people. So what we want to do in these schedulers for these cluster managers, we want to take those people and all the knowledge that they have, and we want to build it into the tool and let the tool just do these things, right? What app? Find a server, put it on the server, record where you put it, update a database that's not a spreadsheet. Maybe you could if you wanted to. But that's what we want in an automated scheduler, right? Let the computers do the hard part. A bit of level setting first. What is a container, right? So a lot of people were introduced to containers via Docker. This is actually a pretty good thing, is that Docker made containers very easy to use. But a container is just some technology in a Linux kernel, right? So when we talk about containers in the classical sense, or in the sense of a cluster manager, we're really talking about application containers, right? Application containers are different from system containers. If any of you have experience with like web hosting, you've probably been using containers for a very long time to give people like $3 web hosting. Like 5 years ago, how can you give people $3 web hosting? It's because you're taking a machine and you're using containers to just give them an isolated view of that server. So you can make really cheap machines that way. But in this Docker community, and what we're talking about with Kubernetes, we're talking about application containers. And the difference with those is we don't expect you to log into your application via SSH. We want you to kind of package things, maybe one app like Nginx or your PHP app in per container. And they should be lightweight. Unfortunately, a lot of people are getting their experience building a container with like from 2 gig operating system and then a bunch of statements to build up your application. And you end up with these 2 gig containers. That's just way too big. There's slightly better ways of doing this, and we'll talk about that later. An application plus its dependencies equals an image. It's just a root file system, packaged in a tarball usually, and a config file on how to execute that particular image. And then the runtime managers, like Docker and Rocket, and there's some other ones, LXC, those are runtime environments that handle some configuration for you, right? C groups and namespaces, it can automate creating those things for you so you don't have to specify them yourself. So that's what a container is. In this talk, we're going to talk about CoreOS Linux. So CoreOS came out about 1.5 years ago, and it was optimized for containers from the get-go. And what does that mean? We basically started with Linux, systemd, and we picked a container runtime and said, that's it. That's all we need to get this done. And a lot of people were taken aback by this by saying, wow, I want to put my Emacs on there and my web browser. It's like, no, you can't. We don't want you to do that. And the analogy I use is like if you were familiar with like a gaming console, like a PlayStation. The developer that builds the games that you play on the PlayStation, they don't develop it on a PlayStation. They develop it on a big, strong dev machine, and they render the video game. And when they're done, that disk or that downloadable image, that's the artifact that you run on the PlayStation. So why are we taking general purpose machines and putting them into production, right? We should probably have something that's like purpose built just to run the application, not develop applications. So GCC on the server is probably not the best IT in the world. There's no package manager in CoreOS. Can't install anything extra. You could use Docker or Rocket as your package manager, but that's not the goal there, is to run your application. Automatic updates. So in CoreOS, the file system where all the apps are installed are read-only. You can't install anything there, and we don't want you to depend on anything there. There's no Ruby, there's no Python, there's no Java. So what this means is that it's not our fault if you depended on something on CoreOS because we told you not to. And since we have this contract with the user, we're free to upgrade in the background. So as your server's running, we're periodically checking for updates, very similar to the way Chrome does it. Matter of fact, almost exactly the way Chrome web browser does it. We use the Omaha protocol. We see an update. We install it to a second partition. If any of you are familiar with like networking gear, a lot of the gear does the very same thing. And then we reboot into the second partition. So we do this atomic update. We keep all your applications and data on the read-write partitions. That's your world. That's your data, separated from the OS itself. This is another important point. CoreOS is rolling releases. So for instance, kernel 3.19 is the stable kernel right now. We roll 3.19. When 4.0 becomes stable in a couple weeks here, we roll 4.0, right? So we keep up to date with these things. All right, etcd. etcd is a distributed key value store, very similar to console, but we shrunk it way down, and all it does is key value. It gives us the primitives to do things like distributed locks that you can build leader election on top of. And the goal of etcd is to store your configuration data. That's it. We build a lot of tools on top of this because this is a problem that you have when you have a cluster manager or something that manages network links. You need to store the routing tables, the state of the cluster somewhere, and we happen to do that in etcd. And we use etcd, and we want the consensus provided, the strong guarantees provided by etcd, mainly so that we can have the whole cluster agree on what values are at a specific time. Flannel. Flannel is our etcd-backed network fabric. So we could call this SDN if you wanted to do some enterprise buzzwords. But what Flannel does for us is it allows us to automate the configuration of Docker containers across multiple hosts so they can talk to each other. This is the networking model required by Kubernetes. Everything on a cluster, the host and the container, are actually first-class citizens. They all have addressable IP addresses. And the benefits of doing that is that we don't have to treat servers different from the application. It's really great when you start doing application tracing to know exactly what app is producing that data. There's optional overlay networking. So if you're in a bare metal data center, you may not want like the UDP overlay, right? Why would you want to do a lot of networking stuff in user space? That's way too slow. You're running a data center for a reason. You want performance. So in those cases, Flannel supports multiple backends. We can go in allocation mode and host gateway. And in those modes, we just configure the subnet. So you give us a /8, we chop that up into smaller /24s that we can assign to the host and allocate IPs to containers from then on out. And that allows you just to integrate with your standard gear. So if you have some Juniper gear, some Cisco gear, you can have, you can just do some normal layer 3 routing to get traffic to flow between the cluster with no encapsulation on top. If unfortunately you're in like a cloud environment where you can't necessarily deal with the L2, layer 2 networking stuff, we do have some overlay stuff. You can go UDP or VXLAN to kind of give you this way of like in a public cloud, building your own private network on top. And then we'll talk about Fleet. So Fleet is a highly available distributed init system based on systemd, right? We talk to the single endpoint, and it schedules units on a machine. So without Fleet, you would log into a server, yum apt-get install Apache, maybe make a service file for it if you're using systemd, put it in the right place, and do servicectl Apache start, or the other way around. And Fleet just says, forget all that. Just talk to Fleet. It'll pick a server for you, or you can be specific and say, I want a server with this ID to run this particular unit. And Fleet basically lets you do this at a cluster level versus the command line. And it also serves as the machine database for CoreOS. So let's look at Fleet in action. So, like again, I provisioned a bunch of machines. All right, so we have 4 machines on the network. Those are their IP addresses, and they have some metadata. They're just called Kubernetes. What you don't see in this output is the etcd server. Etcd is a special snowflake. It is the source of truth for the entire cluster. Don't schedule no more workloads on it. So I have it running on a different VM that's not part of the worker pool. If I do -L, you'll see that the machines, these are the machine IDs that when a machine boots, systemd assigns it a unique ID, and we can address machines that way. Now, we want to stand up a more advanced scheduler. So what we're going to do is use Fleet to deploy parts of Kubernetes. So the first thing we need to do is set up some networking between these machines. So we have these 4 machines, and if we were to deploy containers now on them, they won't be able to talk to each other across hosts. This is mainly because of the default Docker networking model. There's a bridge, some virtual interfaces, and a random IP that isn't routable in the network. So we need to solve that problem. So what we can do is use unit files. So one unit file we have is the Flannel unit file. This looks just like a normal systemd unit file. What we're seeing here is that we're going to use etcd to store the configuration of Flannel, meaning here's the subnet that I want, here's the start and end range of that subnet, and I want to use the host gateway network configuration, meaning Flannel will just update the local routing table on each Linux system so that way we know where the next hop is for a range of containers, right? This is what Flannel will do for us. And then down there we have the execute start, and basically we're saying, hey, Flannel startup, you handle the IP tables entries, and no, there's where etcd is on the network. And then here's some Fleet metadata. So what we want to do here is like we need to run on every single server, global equals true, so we don't need to keep track of our machines. If there's 10,000 machines, that means all of the machines in the cluster that match that metadata. So everyone that is role Kubernetes will get Flannel installed. So let's install it. So we'll do fleet start units Flannel. So that's it. And now every machine on the cluster should be running Flannel. And we can verify that. List units. All right, so now every machine is running Flannel. It's up and running. So now we've done a bit of work. They should have all checked into etcd, figured out what their subnet should be, and configured themselves. And we can validate that really quick. etcd ctl ls. And we do a recursive lookup on that. All right, so let's just see this really quick. So each of those servers came up independently, found etcd, figured out what their subnet was, wrote it to etcd, and this becomes a route entry for all the other servers, right? So we can do etcd get, and we can get one of these entries. So each server on its own independently writes this value into etcd. And what happens is all the other Flannel listeners are watching for this namespace for any changes. A new server shows up, it needs to update its local route table so it knows how to route to those containers, right? Now the next thing we need is something to execute our containers. This could be Rocket, this could be Docker, this could be Lattice from Cloud Foundry, could be anything, LXC. We're going to use Docker in this case. So very same thing. I have a Docker unit file. And here's the Docker unit file looks like. I'm going to run Docker in the daemon mode. I'm going to use the overlay storage driver. I'm going to listen on the local socket because I don't want to actually deal with Docker over the remote API. There's a lot of people in the world right now that have their Docker remote API just open on the public internet. That is like so much fun. You can just like deploy your Bitcoin miners to their servers for free. So thank you guys for doing that. If you're part of that crowd, thank you. And then we have a registry actually running on my laptop, right? So now I have a Go implementation of the Docker's new registry for Docker 1.6 that just came out. So I have it running as a service on my Mac. So I'm going to allow insecure access to that. So it's like behind the firewall in the data center. You'll notice that I don't have any internet access on my laptop on purpose. And then we have this thing here where we say we want the Flannel subnet. So we're going to have Flannel tell us what our subnet range is. Because the way Docker works, every time a machine joins or Docker spins one up, it gives it an IP address. Right? And then we're going to set our MTU to kind of line that up. And we need to also run on every machine. So let's deploy that. So we'll do fleet start units Docker. All right, so at this point, we now have fleet and Docker running on every machine in the cluster. Now the nice thing about globals equals true, we add 10 more machines later, fleet's going to automatically deploy all the global units. We don't have to take any more action. This is like declaring all of them, even though we don't know what all of them are right now. All right, so now we kind of got the foundation in place. Now let's talk about, so Fleet's really good at that. It can schedule, low-level things and replace systemd at a cluster level. But it doesn't have all the smarts that a really advanced scheduler has, right? It doesn't have, there's not a lot of dimensions into the way it schedules. It doesn't take CPU performance into consideration, memory usage into consideration. That's where Kubernetes comes in. So Kubernetes and all these things are open source project. This is an open source project from Google. This project is based on lessons learned from operating Borg at scale at Google for the last decade. They just produced a white paper on Borg and how it works. And Kubernetes is basically an open source implementation of this global scheduler that sits inside the data center. A lot of people refer to this as a data center kernel. Some people may describe these as like a data center operating system. I kind of like the kernel analogy, mainly because you still need user land around this kernel, right? This thing knows how to schedule resources to things, give you views on these things, but you still need to build some tooling to integrate into the rest of your stack, right? If you have some real networking gear, you're going to have to plumb those things together. So it's a container manager, scheduler, and service discovery. That part is important because since service discovery is built into the cluster manager, you don't have to build any sidekick toolings when you start deploying containers to tell them, register them somewhere. Kubernetes handles that. It started the container. It knows where it is. And it does some really intelligent service discovery mechanisms by using labels. So labels mean you don't have to commit to the name of this service right now. So you may deploy a service and say, hey, this is a web service. It serves credit card data. And then you would be in jail. But that could be one of your services. What Kubernetes does is let's not hard code things like that. Let's just give it a set of labels that we can add and remove later, and then we can just classify a service by a collection of labels. This is really, really powerful when you start talking about service discovery. on the fly, we can adjust the service discovery based on just labels. We can find things based on labels. And we'll see this in a demo. Everything is API driven. There is no language. It's strictly JSON that you say what your intent is. Kubernetes works it out. If there's something Kubernetes can't do, then we need to add that logic into the components that make up Kubernetes. We're not going to give you the power of saying for this, in this, if this, do this. None of that. Purely declarative. You say what your intent is. We enforce that intent. There's agents that monitor for state changes. So on all these machines, there'll be agents that watch the API server to figure out what should I be doing. What applications should I be running? Is there any IPs that I need to proxy for? That sort of thing. At a high level, Kubernetes has these 4 main resources. There's nodes, the systems that provide resources that we can schedule to. There's pods, and a pod is a collection of containers. So if any of you dealt with Docker before, you kind of specify, hey, here's a Docker container that does some work. But we all know that an application is usually composed of multiple containers. You may need Nginx, your Ruby application, and maybe this thing that does migrations by looking at the file system or sharing code with the Ruby app. So what we need to do is deploy those things as a collection, as a single unit. And that's what a pod represents. It's a single unit of 1 or more containers. And we can take that single unit and we can give it to the scheduler and ensure that they're co-scheduled to the system together versus breaking them down and then having to figure out where they are. Replication controllers are interesting. They're like the autoscalers for your application. These things take a pod template. You describe what this collection of services look like. And it keeps track of how many you want. If you want 2 of them, its job is to keep track of those by looking at labels of pods on the network. If there's too few, it adds more. If there's too many, it reduces some. That way, if someone spins something up out of bound by talking to the API directly, the replication controller will notice this and kill that thing to keep you at the desired state. And then there's services. Services is the high-level primitive for service discovery. So what you do is you basically assign a VIP. It gets an IP that all the services can use. You can also use DNS. But in this case, I'm going to talk about an IP address by default. And this IP address is associated with the lookup in the API service. So if a node hits an IP, Kubernetes will do a lookup to find all the pods that match a set of labels, get those IPs in port, and then proxy the traffic for you. So then you can freely move things around without trying to orchestrate the whole world. Here's what a pod definition looks like. It's declarative syntax, just JSON. This is a pod object. I'm going to use the v1 beta 3 API. I have some metadata. The name of the app is this awesome app that I built properly. Some labels, like it's in production. Here's the spec. So this thing doesn't have any volumes, and it is composed of only 1 container. And the image name conforms to the Docker spec, where you put the registry and the namespace of that container. And then we specify some ports and an image policy. And there's some other things you can do around policy. Now, every user in the cluster can get their own namespace. So if you want to say, hey, here's your view of the world, maybe that namespace is testing. Another namespace is QA. Or it could just be namespace based on department. Whatever you want to do, these objects land in a namespace, default by default. And Kubernetes will enforce that this pod lives somewhere. All right. Here's the components that make up Kubernetes. It needs etcd. This is where it stores its cluster state. It needs an API server. Everything goes through the API server. When you make changes to the cluster, you go through the API server. All the other components, they watch the API server. They don't know anything about etcd or the backend. Then we have these replication controllers. These are standalone binaries that run within the cluster, and their job is to talk to the API server and figure out is there anything it needs to do. Then we have a scheduler. So the scheduler is a global thing that when you submit work, pods, or replication controllers, its job is to find the best fit in the cluster to run this thing. And then we have a proxy. The proxy is unique. It runs on every host, and its job is to help with service discovery. When you use one of those virtual IPs, they're not actually tied to a Linux interface or anything. It's actually an IP tables rule. So when we see a destination IP that matches that, we actually proxy it to the proxy server running. It does a dynamic query to Kubernetes to see what labels match that IP, and then starts to do proxy of the IPs. And then we have the kubelet itself. This is the thing that runs on each server, each worker node, that knows how to talk to Docker and do the things that's been told by the scheduler. right? So everyone has their role in life. You can pull one of these things out and roll your own. So I've written little miniature schedulers and miniature controllers that do things like, hey, do not even allow work to be scheduled until someone closes this ticket in Jira, right? You can do whatever you want with these things. They're all pluggable. Just pull them out. All you have to do is talk to the API server. All right, so let's provision Kubernetes. So right now we have Fleet running, we have Flannel, cross-container networking going on, and we have Docker in place. So let's spin up Kubernetes. All right, so we're going to use Fleet to do this again. What we want to do first is I'm going to pin etcd to a specific machine, mainly because it has persistent data, right? So what I'm going to do now is list all the machines. Now, there's a different way we actually do this in production. We don't pick a specific machine. We just let it schedule anywhere, and we have the other dependent services follow it. But I'm going to pick a specific machine to show you that you can actually do this. So we'll pick the one with the oddest IP address, .20. We'll take its machine ID. And what we're going to do is we're going to look at the Kubernetes etcd, and we're going to assign it to a specific machine. So when the Fleet scheduler looks at this, it's going to say, all right, what rules are here? It needs to be a Kubernetes node, and it needs to match this machine ID. And this is just a etcd systemd unit file, right? So what we'll do now is a Fleet start the Kubernetes etcd server. So it's going through, it's making its determination, and I know it's going to land on .20 because it has to, right? I've told it to. So it's there now. And then we can look at our units, and we'll see that etcd is now running on this machine. And one nice thing about Fleet, you can do things like Fleet, journal, kube, etcd. And we can look at the logs real time on the server, right? You don't have to log into the server. You know, we can have Fleet proxy the journal on all our machines for us. So now we know that etcd actually started and it's actually running. So the next thing we want to do is deploy the other components. Now, we'll start with the API server. But here, I just want Fleet to figure out wherever kube etcd landed, just put this there, right, wherever that is, right? If etcd were to move, Fleet will also deschedule these things and move them to wherever etcd lives. So we're just going to spin these up with Fleet. So Fleet start, units, kube, API server. And I know it's going to go in .20 because that's where etcd is. All right, and then we want to do the same thing. We need the controller manager, which is another binary on the network. And its job is to handle those replication controller objects that we create into the cluster. And that should go to the same place because it relies on it. And that one had a dependency on the API server. And the next thing we need to do is deploy our scheduler. So we'll deploy our scheduler, same thing. Fleet's doing its work. All right, so now we have our scheduler, replication controller, and the API server. Now, the final bits that we need to do is get the proxy on every machine, and we need to get the kubelet on every machine so we have something that can talk to Docker. And these are very much the same as the global units we saw before. So we'll just start those. Start units, and we want to do the proxy, so the kube proxy. So we start that, it's on every machine. And then if you look at this, list units, all right, they're all there. So we have a bunch of stuff now running in the cluster. And a nice thing about this setup is that all the ones that say global, the proxy service, let's go ahead and add one more. Fleet, start, units, kubelet. All right, so that's everywhere. So now when we list files, all the ones that are global, we can just keep adding servers to this cluster, and they're going to always get the global one. We don't have to go back and update this because new servers showed up. This is really powerful. All right, so now that we have all the components in place, we can actually start doing things with Kubernetes. So I can use the kubectl command to do things like figure out how many pods are running. There's none. By default, Kubernetes puts a few services in place. So we know where the API server is. So when we deploy things into Kubernetes, we can use environment variables that will be injected with all the services in your particular namespace. Right? And the next thing we can do is look at the nodes. There's no nodes. Even though we have all these nodes ready, nothing happened. Now, one way I can add nodes is also using the API. Some people prefer this method. So I could just make an API call with this block of JSON. I can say, hey, this node has this IP address, and it has these labels. Maybe that makes sense, but at a larger scale, you want something to automate this. So what I've done is I've written a really quick app called kube register. And what kube register does, it talks to Fleet. Let's look at the unit file for it, kube register. So it talks to Fleet over a Unix socket that's local to the machine. And then what it does is it says, Fleet, anything that has metadata role equals Kubernetes, give me that list of servers and their IP addresses. And then I'm going to hit their health check port. So in Kubernetes, everything has a health check port or an endpoint called health Z. We hit that endpoint, and if it comes back healthy, we'll register it to the API server. I'm going to automatically register. So that way, if we keep adding machines, we just automatically grow the cluster without any manual intervention. So I'm just going to run this as a very small little Go app. It just runs and does this thing. And we're going to make sure we go wherever the API server is, just to make my life easy. So we'll do Fleet, start, units, kube, register. And this kind of just shows how easy it is to integrate with the Kubernetes API. This is about a 200-line little Go service that I built against the API, and it just works. So what we can do now is look at the logs for this guy. Journal for kube register. Not kubectl, Fleet. Right, so it's up and running, and we see in this log that it registered 4 machines for us. And it just stays on the network watching for changes. Anything shows up or goes away, it will remove them. So at this point, we should be able to see all of our nodes. There we go. So all the nodes are now ready on the network, ready for work. Kubernetes is now in control of this particular cluster. So before we deploy applications, let's just set up a real-world example that we want to use here. So what I've done is already I've pixied some machines, some virtual machines. So I burnt the firmware on the NIC cards on these VMs to kind of treat them like virtual, bare metal machines. We have some cross-host networking in place. We also have Kubernetes ready to go. So now, if you're in the ops department, you rack the machines and you get all the networking right, and you may also install the cluster manager. Maybe implement some policies and credentials, and that's the end of your job. You monitor things and make sure that's always up. Then you kind of delegate power to people to start specifying configs that they can talk to Kubernetes with, right? Kind of self-service mode here. Here's a sample app called PGView, very simple app. It talks to Postgres, figures out all the capabilities of Postgres, and reports it back, right? Postgres info as a service. We have some requirements. It needs to be horizontal and scalable. So if we start with 1, we want to be able to scale out to 5, 10 instances of this thing. We want a dedicated Memcache per instance of PGView, meaning I want my own. I don't want to share one with anyone else. I want to be able to cache my results on localhost via Memcache. That means I need to be scheduled together. And then I need access to the Postgres database, right? Like, we don't necessarily want to give this thing a file to say, hey, here's where Postgres is. I just want you to inject and tell me where Postgres is. And then we want this thing to do, that's our automated service discovery. And then we want 0 downtime application upgrades. That's really, really hard. But with the proxy, we actually get a head start on actually trying to make that happen. Here's what the app looks like really quick. If we do a curl to it and we give it a bit of RPC, in this case we call SQL features, we get this response back. So if you were born a while ago, these are some really hot new languages for you. And Postgres still supports them all for some reason. All right, so let's get on with it. So our goal is to deploy this, right? So now you're an operator, you have Kubernetes, and you've given it to your developers. And let's just go through the flow of deploying that application and also upgrading that application and doing rolling upgrades of it. So what we'll do is we'll start with the pod. So we need a pod first, and a pod is like a singleton. We only want one of these, right? Containers don't make your services like automatically cluster aware and highly available. They just give you something that can move around really quick and probably fail really quick. But in this case, we have a Postgres pod. We're going to give it a volume, meaning we want a path on the host in this case. This could have been if you're in the cloud, you can take a virtual disk or persistent disk and mount it to a host first, and then schedule a container there. You can actually integrate with all those things in Kubernetes. To keep this simple, we're going to say we need a host path that has that destination. And then we're also going to describe the container. We want this container to pull from this registry on my local machine on port 5000. We want the Postgres container. And then the Postgres container has that port. And then down here, we're injecting some environment variables. Don't do this in production. This is like me putting the password for Postgres in here just to make my life convenient. There's better ways of doing this. Normally, I wrap things in etcd, pull things down, and configure it. But in this case, this container is going to take on that password for the Postgres user. And then down here, I'm referring to the mount point described earlier and bind mounting that into the container at runtime. And then down here, we have some basic policy stuff. So what we're going to do now is we're going to tell Kubernetes to deploy this pod. So we'll do kubectl. We want to create pods Postgres. Right? So now the Postgres pod has been created. So we can do kubectl get pods. So it's in pending mode because it's actually downloading the container from the Docker registry running on my laptop. And now it's running, right? But we don't want to use this pod IP. So every pod in the Kubernetes cluster gets an IP from that range that Flannel set up. But we don't want to use this directly, and we don't want to give it to anyone directly, right? We want to give them a service IP instead. So what we'll do is we'll create a service for it. Here's what a service looks like. Again, declarative. You would say, hey, here's the port. We don't know what the IP is yet because we're going to get it from the service portal. So the Kubernetes API has a range. They could be public IPs or they could be private IPs that will allocate when people create a service. So we have a block sitting there. If I submit this job, it's going to give me an IP back. And it's going to be bound to this port. And it's going to look for any containers that have those labels, only those labels. So if it has 10 of those labels, these two will match, and then we will proxy data to it. You can also do sticky sessions or sticky affinity if you want. So if you have multiple and you want clients to stick to the one they land on versus round robining, you can do that. So we're going to create a service. So kubectl create services Postgres. So now we have a service. And when we look at this service, get services, you'll see that we got this VIP virtual IP from the 10.10/16 range. Now, for a lot of you that are familiar with networking, there's no way I'm going to be able to reach this from my Mac. I'm on this L2 network, 192.68/16 network, so are the containers. I can't hit that IP right now if I try, right? So if I were to do this, psql-h, what was this IP? Let's grab it. Let's try to hit this IP, -u Postgres. We can't hit it, all right? So this is where basic routing comes in. So what you would do at your higher level parts of the cluster, you would add some routes. Now, normally what we do in this particular model, we'll load balance this IP to wherever the pods live, or just all the servers and let the proxy server give us the next hop to where it actually runs. So what I'm going to do now is just add a route really quick. So I have this thing that just a little script that adds a static route for me. So this static route is anything going to the 10.10 network. Just go to this host here. It doesn't matter what host in the cluster because there's a proxy that will just send me to the next hop, right? So I just need to just route my traffic somewhere within the cluster. So now that I have my route in place, we can try this again, and it works. What's the password? There it is. So it's CoreOS. So now we're into the MySQL Postgres database. And now we have a service IP for it. So now, how do you use this service IP? Well, let's look really quick at the PGView application. GitHub, Kelsey Hightower, PGView. And we'll just look at, ignore all this source code. But here's where I look at my credentials. I can say Postgres_service host and port. Whenever you deploy a pod with Kubernetes, it injects all the service IPs and port in your namespace. So anything that you're authorized to see, it will just give you the username and password how to get there. There's also configuration management built into Kubernetes. So you could say, when I deploy this container, give it this configuration settings. And then what Kubernetes will do is two options. It will either mount a temporary volume into the space that you specify so that your app can just look on disk for a file that has all the stuff that you want in it, or allow your app to just make a HTTP call to grab the configuration. We're just going to use those service environment variables. So now what we want to do is we won't use a pod this time. We're going to use a replication controller. So here's a replication controller for the PGView app. This is a stable version of the app at version 1. Now, this one's a bit more complicated. mainly because we're going to have a high-level controller that we're describing. And that controller has a specification. Mainly, we want one of these things on the cluster network at a time. Here's a selector. We're going to watch for all pods that have those labels. And that's the only thing that this controller cares about. Here's a template on how to build pods. So if you see that there's too few pods, use this template, give them these labels when you create it. And in this case, we have multiple containers. So the first container is our PGView app that comes from our Docker registry. It lists on port 80. The nice thing about Kubernetes, since every container has an IP, we don't have port clashes. So if everyone wants to listen on port 80, so be it. There's no clashes that you have to deal with. We can also give it some resource limits. These are arbitrary. These are a bit weird because with C groups on Linux, if you say, hey, 1,000 shares of a CPU, and someone says 10,000 shares of a CPU, everything gets relative. So you got to be careful on how you use these. And then here's the Memcache container that we also want deployed in the same pod. And Memcache will just come from the same Docker registry, and it will listen on that particular port. And we also give it some limitations here. Kubernetes is a bit smart about scheduling things. It will take some of those things into account. If you register a node with, say, only 1,000 CPU units, when you get to that limit, no more pods will be scheduled there. It does some basic bin packing. All right, so here's a pod. So now what we'll do is instead of launching those pods, one by one, we'll just launch the replication controller and let it manage the number of pods in the cluster for us. So we'll do kubectl create-f. We want to do replication controllers, and then we're going to do the pgview stable v1 controller. So now that's up and running. So now we can do kubectl get replication controllers, and here we have one in play. This thing wants one replica of this. So if everything's working right, what we should see is a pod being created. And this pod kind of gets a random name here. And what we do is we see that it's actually running. That means Docker has pulled both the PGView app and Memcache. And if everything is working with service discovery, it should also have the right IP and port to Postgres because we use the service VIP here. So again, we don't want to give people the IP to our pods. So we're going to create a service for PGView because we may scale this thing. So the service looks pretty much the same as we saw before, so we won't look at it. But what we'll do is just create a new service for PGView. Now, this service is very, well, let's look at it. This one is a little bit loose. It says that it only cares about things in production that are named PGView. Right? This is good because now if we come up with another controller that has a different set of values, mainly for a new version of the application, this same proxy can be used to send traffic to both since they match the set of labels. All right, so now that we have the proxy in place, we should get a new VIP. And here it is. So here's PGView. We have a VIP. And now we can test to see if this works. So we should be able to do curl, hit this thing, make an RPC request. Let's just get the version really quick. All right, so we know we have 1.0 of the application. And also let's test to see if the SQL is working. So we have a SQL features API endpoint. So we hit this. By design, I introduce a 10-second sleep to mimic a very slow query. The query comes back. It's a lot of data. And if we do it again, Memcache kicks in. And now it's fast, right? So our application is working. It's using the database. It found it on its own. We're doing our thing. So let's see what customers see, right? So customers are using this application now. True, do that. And then we'll sleep for a minute. So we're just going to see what customers see using our app over time. All right, so our customers are hitting Postgres. We're happy we got one instance of the app. It started getting popular. Now your mom is using the service for some odd reason. She deployed Postgres. That's pretty cool if your mom's using Postgres. So you're hitting the service. It's doing its thing. And now what we want to do is scale it up, right? You've earned the right to have more than one instance in our cluster. Sweet. So how do we resize it? Well, we could update that definition and check it in. Or we can actually just talk to Kubernetes directly and say, hey, for that controller, I want you to resize it for me. So let's do kubectl. And we're going to use the resize command. And then we want to increase the number of replicas to 3 from 1. And then we want to do this for replication controllers, PG view stable v1. Yes. All right, so it's resized. So what does that mean? So now that it's been resized, so one thing you do is you see that the definition, the spec inside Kubernetes has changed to 3. Right? Now this is where the replication controller steps in. It says, whoa, the state has changed, real time. We don't have to do any pushes. It's doing a full-time watch. The state has changed. Now the state has changed. Our job is to make it so. So now we have 3 of those things running on the network. They're all up and running now. And they've all done the same things, and they spread themselves out across the host. We don't really care because we're not keeping track. We've just implemented the definition of you wanted 3, you get 3. Using the same template, same version running. What does our customer see? It just does its thing. The proxy is handling things for us. So the proxy will only add things to its backend as they come alive. If you have a health endpoint on your apps and services, it will check that health endpoint before adding it to its proxy pool. So the customer doesn't see any changes here. So now life is good, right? You have 3 of these things, and now you want to upgrade to 2.0. All right, so I don't trust anyone writing code to get it right the first time. So what we're going to do, we're going to give you a canary. We're going to give you one of the new things, and we're just going to mix it with the existing traffic to see if it works. If it works, we'll consider rolling out that new version across the cluster. So one very popular pattern for doing this is the canary pattern, right? So what we're going to do is use a canary controller that looks just like our other controller, but one difference. It uses a new version of the image that we want to deploy. And we also tell this new controller that it should only be concerned about things inside of its controller. So add a new label here. So we'll do PG view, and then we'll do the canary controller. And here's the difference with the canary controller. It only cares about things that have this thing called, a new value called track equals canary. The other one cared about track equals production. So they won't get confused and start fighting each other for ownership of those pods. And the only thing we have different here is just the version of the app. We'll do 2.0 here. So we're ready. We're going to go ahead and do this canary. We're going to see if this thing will work well. So we'll do kubectl, and we'll just do create. By the way, you can do all this stuff with the API if you want. I'm just using the command line, make it super easy for myself. So we'll do a replication controller, and then we'll just do the canary one. All right, so now the canary controller is up. And then we've told it, look, we just need one instance of 2.0, and then it makes it happen. So kubectl get pods. And we see the 4th member in play at the top, track canary. But look at the container that it's running. It's running 2.0. If we go over to this machine, notice what the customer is experiencing now. 2.0 shows up. So 25% of our traffic now is getting the 2.0 app served, right? So no downtime, no talking to 2 different teams. Things are working. The world hasn't blown up yet. We're good. So now we want to roll the entire cluster. Now, some of you may be asking, like, how does this thing actually proxy, right? Because remember, we're using that set of labels. So if we do, let's say you just want, this customer's like, look, I only want the new features. I don't want to see this old stuff. Well, how can we do that? Well, we can just create another service, right? So if we look at services, we'll see that there's a PG view canary service. And then the set of labels it matches is a little bit more specific. Things that have track equals canary will I proxy for. So let's see what happens if we create this guy. Create-f services PG view stable canary. So now that we've added this one, we get kubectl get services. Now with the slash. So we get a new thing come on saying, oh, for track, we'll give people this VIP. So we can make a new DNS entry pointing at this particular VIP, and then come over here and say, all right, customer, curl, hit this thing, RPC. Let's just look at the version. And it's 2.0. So everyone hitting that endpoint will get the dynamic label query that's a little bit more specific and only see these pods. To me, that's really, really powerful. We're not saying this is a service. We're saying this collection of things is a service. So later on down the road, someone adds a new set of things that need to live in and provide this service. You can add and remove a label real time. This also has a lot of power if you want to debug something. Let's say something is happening in production. You don't want to turn off the machine or container doing its work. You can remove a label, which will cause the replication controller to say, oh, whoa, I'm missing one. And it'll spin up a new one and ignore this other one because it doesn't have all the labels to meet the requirement. And now that particular container is offline, but still up and running. You're free to log in and do whatever you want with that. All right? All right, so now that we have our Canary running, we have this other service for people that want to use 2.0. And now we need to roll the cluster to the new version across the board. Right? So there's a bunch of API calls you can do to orchestrate this for you, but there's also things like update controllers that you can write. So you may say, do my update at this time of day, and then if there's any failures, put back the old one. You can do whatever you want here. I'm just going to show a very simple one that's built into the tool. So kubectl, we're going to do a rolling update, and then we're going to give it an update period of 3 seconds. And then we want to update the pgview stable -v1 controller, and we want to give it a new one specification, mainly the v2. pgview stable v2. All right. So what's happening here now is our command line tool is orchestrating a couple of API endpoints. And the reason why they're all separated APIs, there's no way we can know the workflow for everyone. But the workflows are rich enough to allow you to do this. So what this is doing is taking both replication controllers, on one of them de-incrementing its replica count, and the other one increasing its replica count. Right? So we can just kind of make the switch. One dies, the other replication controller brings another one online. And we just do this at the same time until it's complete. And what are the customers seeing here? Right? We're not dropping packets. A little bit more than half of our traffic is now all running 2.0. And we just keep going and keep going. And then eventually, we should see 2.0 across the board for all customers. That's it. We've rolled the full cluster. Everyone's been upgraded to the new version of the application. And with that, that's the end of the demo. Thank you. I guess we'll take questions. Cool. Okay, so he wants me to kill it. The question is, can you kill one of the containers and you want to see it bring it back, right? Because it got really hand wavy, didn't it? Yeah, I was like, wow, you're this guy was in here hand waving. Don't do that on Twitter. Okay, so what will happen is kubectl get pods, right? So you want to kill a pod, right? So let's take this pod, this guy. Sorry, it's not me, it's him. kubectl delete a pod, and we're going to delete that one. All right, it's gone, right? But the thing is, the replication controller is like, don't matter, coming back. So it's pending. So we have to schedule a new one because it doesn't meet our definition of requirements. And now it's running again, right? So if someone deletes one of the pods, the controller says, you said 3, I see 2, and it puts it back, right? So it just enforces state all the time. Now, if we were mid-flight there, we would probably drop the packet. I mean, you killed the thing. But you can have hooks in Kubernetes. So when we delete a pod, we can have some hooks to call on the way out. Maybe one of the hooks is, well, wait until I finish this connection. I just won't take any more. And then maybe it needs to clean up a little bit. We'll allow you to do that in Kubernetes, right? So you can delete pods. And the same thing happens if you remove a server. Yeah, so there's signal handling, so we do send a sig term to the machine, but we also explicitly, you can define other actions that need to happen inside the spec for your particular pod, like do this other thing over here, right? Good question. Here and then here. Doesn't matter. It works with IPv6 as well. So do you want to look at the rules really quick? I said I wouldn't log into the server, but the talk is over. We're now allowed to log into the server. Okay, all right. So I don't want you guys to call me out like, dude, you logged into the server. I saw you. So let's just do that now. We'll log into one of the servers. It doesn't matter which one because the proxies is the thing that manages the IP tables on these things. So we log into this thing, and then we can do, man, my IP tables foo is rusty, so if I'm off, I apologize. We want to look at the NAT table, IP table. Man, that'd be sucky if there's only one of them. Like, where's my table? Yeah, Yeah, here we go. We don't want to resolve these names. Okay. So what we have here is, you see all these like rules. So there's the Kubernetes services. Here's our Postgres one, Postgres PG view. And what it does is, so none of these IPs in this 10 range, if you notice, none of them are assigned to any of the interfaces, right? They're not there. You don't see Flannel there either because Flannel's not doing any encapsulation. So what happens is, when IP tables executes, we just have this, we filter the rule, the packet comes in, we see what the destination header looks like. We send that destination header to the proxy on a random port over here. So in this case, the proxy is binding to port 45,000, blah, blah, blah. And it will say anything that comes into this destination IP is going to go to Kubernetes and say, hey, this IP came in. Could you give me the pods that belong to it? And do its proxy that way, right? So everything happens here. And the nice thing about this particular pattern, if you have a higher level like router, F5 or something like this, you can tell F5 what the next hops are for these services, right? So I have some integrations I've done where you can build custom plugins. So I've done this for Nginx and Lua, where the backends, you see an IP come in, you can have it dynamically look up the backends and cache it in Nginx. So it's really, really flexible here. Cool. I think there's a question here. Yeah, so let me go back to the slide. So see, there's something you have to do too, right? So your job is you got to handle the failures, right? So a lot of people that are operating in distributed environments, they understand this very use case. I'm doing this database migration. What's the responsibility of the app if this happens, right? Maybe when you start your database migration, you can inform other people using something like etcd and say, hey, migration's underway. You need to go in maintenance mode and don't process any writes or reads or something like this, right? And maybe handle the failure if you are mid-migration and you get clipped, right? There's databases that handle this better than others. But if you're in that situation, you have to handle that orchestration. Like that is not a cluster manager's concern that you chose to use something like MySQL or Postgres that can't handle being migrated or moved and it has to have downtime this way, right? There's patterns for doing these things, but Kubernetes is of no concern. That's a different level of the stack. So there are people that have some tooling around this. There's a company called Compose.io. And a lot of the patterns you see for this particular use case, you can introduce a proxy in front of your database that takes all the connections. That proxy, you can tell, like, hey, we're going into maintenance mode, block connections or block queries, maybe send them to the caching layer, do your migration, and then bring things back online. So that way you can respond with, hey, database is out of service. Your app should be built in a way that it can handle that happening periodically, and you're free to do your database migration there. That's going to be different for every company depending on what their needs are. That should not be encapsulated in Kubernetes, right? Maybe you could write a controller that does it, right? You could have a smarter controller that says, oh, that's a database thing. I'm going to go through all of these steps before I do anything. That controller, you can just pull it out. Before we go 1.0 in Kubernetes, the goal is to have you have the ability to put custom objects in Kubernetes to write your own controllers. For example, the OpenShift team has written their own deployment controller that's really smart about handling multi-tier deployments. And then they can have their own JSON blob to describe that multi-tier deployment. And then they launch their own binary that will watch for multi-tier deployments. You can do the same thing for database orchestration, right? So you'll probably see, and if you do it, you can share it with the community, and then people can just run it in their cluster. Thank you guys for attending. I'll be around.